This is 16.6, question number 3. We're going to again find the area of this function. This turns out to be a plane in the first octant. Once again, we've got other techniques that we could apply to this, but what we're going to look at is parameterizing it according to 2 dimensions. So in this case, we're going to take the easy way out. Probably the easiest way to find a parameterized function of 2 variables is simply assign this to the first 2 variables. So u is going to be x, and v is going to be y. And then, of course, we simply solve this guy for z. So z is actually going to be equal to 5/2 minus x over 4 minus y over 2. And then, of course, x and y are actually u and v. So there it is. Because the function is easy to explicitly write in terms of z, parameterizing it is just making ux, vy, and z into whatever the function is defined as in terms of u and v. Now, this doesn't work all the time, and sometimes the z function has a nasty square root in it. So this isn't recommended all the time. When your function is round, it's usually better to drop into some sort of polar representation of it. But this will work for this one. Okay, so there's r, and remember what we're ideally looking for is a double integral of ru crossed with rv. We want the magnitude of that dA in our parameterized variables. And again, what does this guy do? Well, it builds up all those little parallelograms because the vectors u and v both lie within this plane. I know that their cross product produces a normal to the plane, and also the cross product's magnitude is equal to the area of the parallelogram. So if I add them all up, I'll get the area of the surface. Okay, well, let's do our u, and that's just going to be 1, 0, and then -1/4. Our v, and that's going to be 0, 1, and -1/2. And then we want ru crossed with rv, and the cross product in this case is going to produce that 0, so it's 1/4. The middle one, that's -1/2, so that's 1/2. And finally, the k1 is just 1. And then we want the magnitude of that, so we're going to take this guy and apply the Pythagorean theorem. So this is going to be 1/16 plus 1/4 plus 1, and the whole thing under the square root. And that turns out to be radical 21/4. So that's what I integrate over these dimensions. And again, in the first octant, we do have to figure out what our dimensions are going to be for integration. So because v and u are just x and y, I know the intercepts of this. If z is equal to 0, we're actually in the xy plane. And if x is 0, y is 5. And if y is 0, x is 10. So that gives me the equation for this side. V is going to be equal to, it'll be 5 minus 1/2 u. So this becomes our upper bound in v. We'll integrate u between 0 and 10. And we'll integrate v from 0 to 5 minus 1/2 u. And then this is our integrand, radical 21/4 dv du. And when we finish this whole mess, this turns out to be 25 radical 21/4. So that is the surface area of that plane in the first octant.